Imagine for a moment trying to build a single universal dictionary that captures, well, every single medical concept. Diseases, procedures, anatomy, everything.
Mhm.
Now, picture thousands of experts, brilliant people,
Huh.
all trying to add to it, change it, simultaneously.
Right, from all different specialties.
Exactly. How on earth do you keep that consistent? How do you stop it from just becoming chaos?
It's a huge question.
Especially when the accuracy could literally mean life or death. It just sounds like an astronomical challenge.
It absolutely is.
Yeah.
And that massive challenge is precisely what the paper we're diving into today really tried to tackle.
Okay.
It's called Scalable Methodologies for Distributed Development of Logic-Based Convergent Medical Terminology. Campbell and colleagues, back in '98.
28. Okay. So this isn't brand new, but foundational.
Foundational, exactly. It hits the core issue.
Yeah.
How do you manage constant change in these enormous medical terminologies like a SNOMED?
Which are basically the backbone for electronic health records and all that informatics stuff, right?
Yeah, absolutely. They underpin so much of modern healthcare IT.
So our mission today, then, is to unpack how these, pioneering methods and tools they came up with were designed. How they aim to make this giant task not just doable, but actually scalable.
Right. Scalable so it could handle lots of different needs, lots of contributors, without everything falling apart.
Okay.
And the heart of their solution was this novel environment they called Galapagos.
Galapagos, interesting name.
Yeah, and it was designed to kind of merge advanced logic systems with the messy reality of lots of people working together, often far apart.
Okay, let's unpack this. From your point of view, what makes developing and maintaining a medical terminology so uniquely hard? Is it just the size?
No, it's far more than just the size, though that's certainly part of it.
Right.
Beyond the sheer number of terms, it's the inherent complexity of representing medical knowledge itself.
How so?
Well, concepts aren't neat boxes. They overlap, they have fuzzy edges, they get defined differently depending on the context.
Like a surgeon might see a condition differently than a pathologist.
Precisely. And it's always changing. New discoveries, new understandings.
So it's dynamic.
Hugely dynamic.
Yeah.
And for any system trying to model this to actually work long term, its development environment needs to scale in 3 critical ways.
3 ways. Okay, lay them out for us.
First, cognitive scalability. The tools themselves need to help the developers.
Help them how? Like, suggest things.
Kind of. By automatically figuring out inconsistencies, or maybe spotting new relationships between concepts that a person might easily miss.
Okay, so augmenting the human modeler.
Exactly. Second, computational scalability.
Meaning the computers don't just melt down as you add more terms.
Basically, yeah. The resources need to keep up as the terminology grows bigger and bigger.
Makes sense. And the third?
And this is crucial, organizational scalability.
The people problem.
Yeah, got it. As you add more modelers, more experts, the effort to coordinate everything, integrate their work, has to stay manageable. It can't just explode into bureaucracy.
That organizational part sounds like the real sticking point for a lot of these systems.
It often is.
Because you mentioned these description logic classifiers. They sound great for the cognitive and computational side, like magic logic engine.
They are powerful, yeah. They can deuce things, spot certain kinds of errors.
But you're saying they traditionally didn't help much with managing multiple people working at once.
Very little, historically. They didn't really offer support for, concurrent modelers or figuring out when 2 people made changes that actually conflict with each other.
And that multi-person collaboration isn't just a nice to have here, right? It's essential.
It's absolutely essential. Medical knowledge is too vast, too dynamic. You need diverse experts, different application needs driving the development.
So you need the collaboration, but the tools weren't built for it.
Traditionally, no. Which leads us to how you even approach the whole design, the philosophy behind it.
Right. The paper contrasts 2 really different ways of thinking about this.
Yeah, 2 fundamental approaches. The first is what they call creationist design.
Sounds biblical.
Maybe a bit. It's the more traditional way. Think preordained design.
Meaning someone at the top decides everything up front.
Pretty much. A single designer or a central group lays out all the principles. Then they supervise closely to make sure everyone sticks to the plan.
So a single blueprint.
Right, a singularity of design. Deviations are frowned upon, discouraged, which tends to lead to homogeneity.
Everyone has to buy into the one true way.
Exactly. Modelers kind of self-select based on agreeing with the core design. And look, this can be efficient for smaller projects, things with really clear fixed goals.
But for a massive, evolving medical terminology.
The paper argues it's just stifling and inappropriate. It can't handle the sheer scale or the fact that we don't even know all the future needs.
Okay, so that's the old way. What's the alternative they champion?
This is where it gets really interesting, like you said. They push for evolutionary design.
Evolutionary. Like Darwin for dictionaries.
Sort of. Instead of a fixed blueprint, the idea is the design isn't finished at the start. It evolves.
How? Through using it.
Through development, through feedback, through people actually building it. It values the accumulation of design.
Accumulation, meaning you keep everything.
You archive individual insights, individual pieces of work. You analyze them, incorporate them, even if they conflict initially.
Wait, even conflicting ideas. That sounds messy.
It can be, but the key is it encourages heterogeneity. Diverse approaches, different viewpoints are welcomed.
Okay, I can see the benefit there. You get a richer result, maybe.
Potentially, yes. It might not seem as neat up front, but the argument is it leads to a terminology that actually meets broader needs, and people feel more ownership.
Right, because their contributions weren't just rejected if they didn't fit the initial mold.
Exactly, but there's a major roadblock to this evolutionary dream.
There's always a catch.
There often is. They call it the local update penalty.
Local update penalty? What's that?
It's this paradoxical situation. Imagine a user or a site invests a ton of effort integrating their own local stuff, maybe specialized terms, maybe linking to other resources like the UMLS Metathesaurus.
Okay, they're enhancing their local version.
Right, they're adding value. But then when the new official version of the main terminology comes out.
I think the biggest headache trying to merge it all.
Exactly. The people who invested the most locally face the biggest job reconciling their changes. It effectively punishes innovation.
Wow, yeah, that would definitely discourage people from enhancing things locally.
Completely. So a core goal of this paper and the Galapagos system was to reverse that penalty, to actually reward local work.
That's a huge shift. So if you want this distributed evolutionary approach, how do you manage people working concurrently, especially if they're working offline, maybe for weeks?
Right, that takes us straight into concurrency control.
Like in databases, making sure two people don't overwrite each other's work.
Precisely. Databases usually group operations into transactions, atomic units of work, designed to keep things consistent.
Okay.
But the traditional ways of doing this, they just don't cut it here.
Why not?
Well, take locking mechanisms like two-phase locking. They work by literally locking data.
So if I'm editing pneumonia, no one else can touch it.
Right. But imagine a modeler is refining a whole complex hierarchy of diseases. This could take weeks, what they call a long-lived transaction, or LLT.
So pneumonia and related terms are locked for weeks. That stops everyone else.
Totally impractical for collaboration. Then you've got other approaches like optimistic non-locking.
Optimistic, how does that work?
It lets people work concurrently, assuming conflicts are rare. But before you commit your changes, there's a validation step.
Right.
If the system detects that your work conflicts with someone else's in a way that breaks the sequential order, serializability, your transaction just aborted.
Aborted. Like all your work is just thrown away.
Poof. Gone.
Ouch, nobody wants to risk losing weeks of work like that.
Absolutely not. Plus, these optimistic methods usually need a central database, which kind of defeats the purpose of distributed work.
So what this all means is the standard ways fail. They demand this strict sequence. They throw away work. It kills collaboration and local enhancements.
Pretty much. They're just not suited for this complex, long-term, distributed modeling environment. We needed something smarter.
Something more semantic.
Exactly. That led to the idea of semantics-based concurrency control.
Okay, using the meaning of the changes.
Right. Instead of just a strict, arbitrary order, you use knowledge about the domain medicine, in this case, to define what constitutes a real consistency problem.
Interesting. How does that work in practice?
Well, one earlier idea was sagas. These are long transactions where if there's a conflict, you run a compensating transaction.
To undo the problem part?
Sort of, yeah. It tries to restore semantic consistency without rolling back everything someone else did, but
Yeah, there's still a pet.
even sagas didn't really give you a way to resolve the conflict and merge both people's work. One contribution still often got effectively discarded or needed a total redo.
Okay, so the leap we need is don't just compensate or abort. Find a way to reconcile both pieces of work using that semantic knowledge.
That's the holy grail.
Yeah.
And to get there, to really identify conflicts intelligently, the paper uses a classic method, Aristotelian classification.
Aristotle. Like philosophy.
Yep. Defining terms by their genus, the broader category, and differentia, what makes them unique within that category.
Okay.
And using syllogisms, that if A is B and B is C, then A is C kind of logic, the system can analyze how properties are inherited.
To see if two changes are really saying the same thing or if they actually clash.
Precisely. Are they semantically equivalent or truly in conflict? Galapagos leverages this heavily. But just detecting conflicts isn't enough when you have multiple versions everywhere.
Right, you need to manage all those different versions and track how conflicts get resolved.
Which brings us to configuration management, something software developers know a lot about.
Version control, like Git.
Concepts like that, yeah. The paper looks at how configuration management models evolved. There's the basic checkout check-in model. Simple, lets you branch off, but merging is often manual and messy.
Yeah, merge conflicts. Fun times.
Then there's the long transaction model, more focused on how a whole system evolves. Transactions happen sequentially in workspaces.
But still has that problem with long transactions blocking things.
And it doesn't solve the local update penalty, because the changes aren't really independent things outside their workspace.
Okay, so what's the breakthrough model?
The change set model. This is the key. Think of it like the long transaction model, but transactions are named independent entities, change sets.
So a change set is like a package of related edits.
Exactly. And crucially, you can extract these change sets, combine them, apply them to different versions or configurations.
So you could take your local changes as a set, get the main updates as another set, and try to merge them.
Precisely. It allows for distributed concurrent changes without needing constant central coordination. And this is what enables reversing that local update penalty. People can manage and share their change sets.
Okay, that makes sense. It decouples the work.
It does.
So after all that theory, let's finally meet Galapagos, the actual system, built on KREP. What's KREP?
KREP is a specific type of knowledge representation system, KL1 style. Think of it as the underlying engine Galapagos used.
Got it. So how did Galapagos put all these ideas, semantic conflict detection, change sets, into practice?
Well, it used KREP's journal to log all the changes. That's vital for tracking history.
Okay.
It used KREP's classifier, that logic engine, to actually detect those semantic conflicts we talked about.
Using the Aristotelian definitions.
Yes. And it stored the full modification history, allowing people to generate custom change sets to sync up their local versions with the main one.
So it really implemented that change set model.
It did. The whole system was built around semantics-based conflict ID and, importantly, interactive conflict resolution.
Interactive meaning humans are involved.
Absolutely.
So what kinds of specific conflicts could Galapagos actually sniff out?
It focused mainly on two types, based on those Aristotelian definitions. First, the multiply-defined term, conflict.
That's when two people define the same term differently.
Exactly. Like our earlier example, modeler A says infectious pneumonia is lung disease, modeler B says it's caused by infection. Both seem plausible, but they define the same term differently. Conflict.
Okay, what's the second type?
Non-unique definition conflict. This is the opposite. Two different terms get the exact same definition.
Like infectious pneumonia and pulmonary disease, both defined as disease affecting the lungs.
Precisely. This signals something might be wrong. Maybe they're synonyms. Maybe one definition is too simple. Galapagos flags it.
Okay, so it flags these conflicts. How does the resolution actually happen? Does the system decide?
No. That's crucial. Resolution needs domain experts, human judgment. Galapagos doesn't make the call.
It just presents the problem clearly.
Exactly. It facilitates resolution. It gives the modelers the info about the conflict, gives them tools to modify the terms, and then helps spread the agreed-upon changes efficiently.
So for the multiply-define term, they might merge the definitions.
They might merge them, or maybe refine one or agree on sequential steps to include or exclude differences. For non-unique definitions, they might declare the terms synonyms.
Or simplify one definition.
Right, maybe make one a primitive definition that needs more detail later. The key is flexibility and human oversight.
This sounds great in theory, but did it actually work? You mentioned it was tested.
Oh yeah, this wasn't just a lab experiment. It got a serious real-world workout in the Convergent Medical Terminology Project, the CMP project.
CMT, who was involved?
Kaiser Permanente, 3 different regions plus the Mayo Clinic. Multiple modelers at each site.
Wow, okay, that's a complex setup. What did they find?
The results were pretty impressive. Over 6 months, 5 development cycles, they tracked over 54,000 transactions.
54,000? That's a lot of changes.
A lot. And the overall rate for that multiply-defined term, conflict, just 2.2%.
2.2%. That sounds pretty manageable.
They deemed it acceptable, yeah. There was one blip, One merge cycle hit 19%.
Oh, what happened there?
That was traced to a huge bulk import of ICD-9CM codes. Basically, dumping in a pre-existing classification caused a lot of definitional overlaps.
So they learned something from that.
They did. It led to a policy change about how to handle those big imports more carefully in the future. But overall, the evaluation showed Galapagos really did meet its goals.
And what's fascinating reading about it is that these conflicts weren't always just errors to fix. Sometimes they were productive.
Exactly. That's a key insight. Some conflicts were semantically equivalent, different paths maybe.
Yeah.
But the classifier logic realized they meant the same thing, like defining abscissa phi in slightly different ways that resolve to the same meaning.
Okay, so those are non-issues. But the others, the semantically conflicting ones.
Those often led to really valuable discussions. The paper gives this great anecdote about flexion, NO.
Flexion, AS. NOS, meaning not otherwise specified.
Right. There was a conflict, and it sparked a debate among the modelers. Is flexion fundamentally about muscles or about joints?
Ah, a genuinely tricky conceptual
A
question.
deep one. And that discussion, prompted by the conflict, led them to realize they needed two distinct concepts: active flexion, NERES, and passive flexion, HERES.
So the conflict actually improved the terminology's precision.
Massively. It became, as they put it, a joint learning session. The conflict wasn't a failure, it was a catalyst for deeper understanding.
That's powerful. It also showed how different professional views could cause conflict, right? The cellulitis example.
Oh yeah, cellulitis of skin with lymphangitis, NOS. Ambulatory care doctors thought about it one way, pathologists conceptualized it slightly differently. Both valid viewpoints based on their work.
Which raises that big question. How do you reconcile those valid but different professional perspectives?
It's tough. And the paper really stresses that letting everyone involved participate in resolving these conflicts was vital for group cohesion.
Makes sense. If someone felt their carefully considered viewpoint was just thrown out.
They tended to disengage. They observed that if modelers felt their work was arbitrarily discarded, they just stopped contributing as much.
So that conservation of design idea from the evolutionary model valuing all input was key to keeping people invested.
Absolutely critical for collaboration.
So the system worked, but no system is perfect. Did the evaluation suggest ways to make it even better? Especially around resolving conflicts.
Yeah, they floated an interesting idea: authoritative domains.
Authoritative domains, like declaring someone the boss of a specific area.
Sort of. If you have a process, say that ICD-9 import we mentioned, that is declared authoritative only for ICD-9 codes,
Okay.
then conflicts arising purely within that imported ICD-9 data might be automatically flagged as, well, uninteresting, maybe just artifacts of the import.
But if someone else's change overlapped with that ICD-9 data,
That would be flagged as interesting for the group to discuss. It's a way to filter out noise, potentially. Reduce the burden of resolving conflicts that are just known issues from a source.
that could definitely streamline things. But even with improvements, we have to admit technology has limits. What kinds of conflicts could Galapagos not find?
Right, that's a really important point. Galapagos, based on that Aristotelian classification, is great at comparing definitions based on their logical structure.
Genus and differentia.
Exactly. But it can't easily detect when two different terms, maybe with unique definitions that don't logically clash, actually refer to the same thing in the real world.
Can you give an example?
Sure. The paper mentions SNOMED originally had two entries for mole and S. One for skin growth, one for the animal.
Ah, same word, totally different meanings. Galapagos wouldn't know.
Not from the definitions alone if they were structured distinctly. Or think about morning star and evening star.
Both are Venus.
Right. But if you define one as last star seen in the morning and the other is first star seen at night, with unique IDs, Galapagos wouldn't automatically know they point to the same planet. The definitions themselves don't conflict logically.
Or complex diseases with different names based on, say, how they're discovered or described.
Exactly. Like non-bacterial verrucous endocarditis and Limben-Sachs disease. They might refer to the same condition, but have definitions focusing on different aspects, associated disease versus underlying process. Galapagos wouldn't necessarily link them.
Which means you still need humans.
You absolutely still need human review, eyeballs on the terminology. It has to be an ongoing part of vocabulary development to catch these subtle but critical real-world semantic equivalences or distinctions that the logic alone misses.
So, wrapping this up, what does this all mean for you, our listeners? We've seen these really clever tools like Galapagos designed to wrestle with this massive complexity in medical terminology.
fostering collaboration, letting knowledge actually evolve in a distributed way that older methods just couldn't handle.
It's this fascinating mix of advanced logic and very necessary human input, managing this vital, constantly changing knowledge base.
And it really makes you think, doesn't it? This challenge extends way beyond just medicine.
How so?
Well, in any field where knowledge is growing fast, where many people are contributing, think science, think open source projects, think policy development,
Huh?
how do you strike that balance? The balance between using powerful computational tools to find patterns, find inconsistencies, maybe even suggest solutions.
And the irreplaceable value of human discussion, diverse perspectives, judgment, and understanding those subtle nuances that, frankly, only we can really grasp.
Exactly. That tension between machine efficiency and human wisdom.
How do we best leverage both? It's not just about medical codes, it's about how we build and manage shared knowledge collectively in the digital age. That's definitely something to mull over until our next deep dive.